In many ways, it depends on your teacher how you learn certain things in math, and sometimes learning it in multiple ways is so much more useful. But learning the concept is like having a pattern you build on in each level, so you do better in higher level math. I wish I knew these things when I was younger. I could have gone further. So I know you guys will go further and one day teach me things. So let's talk about square roots. We're talking about real shapes. So let's pretend we're brick builders and we like squares, and we're going to build a pyramid. So you can have a square, and it's a perfect square, we call it, because the square's definition is that the sides are equal and it has a right angle. Okay, sides could be equal and we can tilt it. It would be a rhombus or a diamond. So we also know the sides are the same. So let's look at first how we do square roots in school. We learn perfect squares, 1 squared, 2 squared, 3 squared, 4 squared. It means 1 times 1, 2 times 2, 3 times 3, 4 times 4. Why? Because they make perfect squares, right? A square with sides 3 by 3, a 4 by 4, a 2 by 2, and a 1 by 1. Okay, so in school we're taught the square root of 4, we break it down as a 2 by 2, and we take out, for every 2, we take out 1, and the answer is 2. So why do we go from 4, break it down, and then why do we only take 2 pairs and turn it into 1? Or why do we take 2 numbers and turn it into 1? Because we're saying if you have a square with 4 blocks, which would be this one, 1, 2, 3, 4, you'd have a 2 by 2, the sides, a 2 by 2. So what's the root of one side? Would be 2. So when we're looking at actual shapes, right, a square is a 1 by 1, 1 squared, and it makes a square. A 2, we can't do that. We get stuck, right? We would call that the square root of 2. Can you make a square out of this? How about 3 of them? Square root of 3. No, you can't, because it's not even where the sides are equal. You're missing some on one side. So let's say go back to 2. You have the square root of 2. And when we punch it into a calculator, it's this number that goes on forever. And that tells us that when we chop this up and make a square out of it, we would actually have to cut this into pieces. I don't know if I could even do it just by doing this, right? But the point is we need to rearrange these pieces to make a perfect square where all the sides are equal. And you know, you'd have to cut and keep cutting and rearranging until you had a square, not a rectangle, right? And if we did that, how much would each side be? Let me double check. Alexa, what's the square root of 2?
The square root of 2 is 1.4142.
Okay, so what we're saying is if we did find a way to cut these into pieces, 1.4 and 1.41 would be how much each side would be. We don't like using this decimal that goes forever, so we just use an abbreviation of it, square root of 2, which implies this number that goes forever, because if you had to chop these pieces, you could never get it perfectly right. In theory, you could pretend you could make a square out of it, but really it's never going to be perfectly right, because an infinite decimal means you could never really get that piece. You can't get a piece of infinity. So when we get to square root of 17, let's say, right? You know you have a 4 by 4, 16 of them, with 1 left over, 1 little block left over. You'd have to chop that up, put it on all the sides, and it would be an infinite decimal, 4 point something, because we know there's 4 in a little bit. And we could never really get it right. But again, in our minds, in our theory, we could rearrange these and find a way to mold it into a square. So really it's possible to make a square with 17 blocks. We'd have to chop it, but using math, we don't have to even do it visually. We can just poof, get a number and see what's done. So an imperfect square means you'd have to chop up the pieces to really make the square work. And the perfect squares go in between the whole squares. The imperfect squares go in between the perfect squares. Look, you start with 1, and then you try 2, doesn't work. Then you try 3, doesn't work. And then you get to the next perfect square, which is 4, 4 by 4. Okay, so square root of 2 and square root of 3, we'd have to chop the pieces up and it would really never fit. So we just call each side square root of 2 and square root of 2, 1.4. Square root of 3, if we chopped it up, each side would just be the root of 3. So when we say the root, we're asking what is one of the sides if you were to build a square out of those pieces. 4, square root of 4 is perfect. It makes 2 and 2. You don't have to cut or chop anything, right? And we can keep going. We can go to 3 squared and a 3 by 3 or 3 squared. There would be 9 of them, right? So really even multiplication is how many rows and how many columns. 2 times 3 is really 2 rows of 3 or 6 little pieces. 3 rows of 3, this is going to give us 9. Square root of 9 is 3, right? Then we have square root of 10. We would add one more and have to chop it up, and we just know each piece would be a little bit more than 3 because there'd be a 3 by 3 with 1 left over that we chop up and put around. So that's what a square and a square root is talking about. And that's why when we have the square root of 9, we say is 3 times 3. Those are the 2 sides. So the answer is what's one of those sides? 3. So that's why we take a pair out. It's asking what is one of these sides. What is the root of this square? And then the reverse. What is this square when one side is 3? 3 squared, a 3 by 3 square gives you 9. What about a 4 by 4 square? We don't want to make squares. Can you imagine taking even a simple number like 10? We mostly know 10 times 10 is 100. Do you really want to count 100 squares and put them on your paper or even, have little pieces? We can even do, off the top of my head, 25 times 25, I think is 625. So you're able to do things you can't even imagine in your brain and count rows and columns in your mind. Quickly as a trick, your brain can compute it. You become a computer. So squares and square roots are talking about actual pieces of squares. That's the first step. So how does this apply to the Pythagorean theorem? Because the Pythagorean theorem is what we use to get the distance formula. So that'd be the second video. What is the Pythagorean theorem talking about? Is it really talking about shapes? And spoiler alert, it is. It's talking about squares as well.